Could an alien civilization be trapped on its own planet? Astronomers have reported evidence of an escaping atmosphere surrounding LHS 1140b, a potentially rocky planet discovered in 2017 that resides in the habitable zone of another star. But with nearly 6 times Earth's mass, could a civilization living there ever overcome its enormous gravity and develop spaceflight? Hello, I'm Dr. Alejo. LHS 1140b orbits a low-mass red dwarf every 24.7 days. It has roughly 5.6 times Earth's mass and a radius about 70% larger than Earth's. It may be the first rocky planet in a star's habitable zone for which evidence of an atmosphere has been detected. It receives only about 42% of the stellar energy that Earth receives from the Sun. It may also have retained an atmosphere and an enormous quantity of water, but the gravity that helps it hold onto that atmosphere could make it extraordinarily difficult for a civilization to live. The Fermi paradox is the apparent tension between the enormous number and age of potentially habitable worlds in the galaxy and our failure to find confirmed evidence of extraterrestrial technological civilizations. In his book, If the Universe is Teeming with Aliens, Where is Everybody?, Stephen Webb presents 75 possible solutions. One is called They Stay at Home. Perhaps some civilizations simply have no interest in space exploration. But what if staying at home is not a choice? What if a civilization could develop radio, computers, and nuclear technology, yet remain confined to its planet because of its enormous gravity? The LHS 1140 system is approximately 49 light years away. In September 2024, astronomers observed the 1140b planet passing in front of its star with a wind-red near-infrared spectrograph in Chile. They detected an absorption feature consistent with metastable helium. The signal appeared not only while the planet was crossing its star, but also before the transit began. It suggests a tail of helium extended ahead of the planet in its orbit. The most likely explanation is that X-ray and extreme ultraviolet radiation from the star is hitting the upper atmosphere and driving helium into space. The escaping gas also appears to contain very little hydrogen. The researchers suggest that the lighter hydrogen may already have been preferentially removed, leaving a helium-rich upper atmosphere. However, the helium signal was not detected when the planet was observed again in 2025. The atmospheric escape may be variable, but more observations are needed to confirm that explanation. This is not evidence of life, of course. It is evidence of an active atmospheric process on a temperate super-Earth. This relates to the cosmic shoreline, a proposed boundary between worlds that retain substantial atmospheres and those that lose them. The habitable zone alone is not enough. An atmosphere may also be needed to regulate temperature and maintain liquid water. LHS 1140b's gravity may have helped it remain on the atmospheric side of this shoreline. Astronomers also think the planet could contain an enormous amount of water, although no ocean has been detected. A dry planet of this mass should be more compressed and denser. Its unexpectedly large radius therefore suggests lower density material. Initially, there were two main explanations. It could have a light hydrogen and helium envelope, or water could represent approximately 9 to 19% of its total mass. The JWST did not detect the prominent spectral features expected from a hydrogen-rich atmosphere, making the water world interpretation more plausible. The planet is expected to be tidally locked, although this has not been confirmed. Much of its surface could be frozen, but climate models suggest that under some atmospheric conditions, an ice-free ocean might exist around the point permanently facing the star. Again, this is a model possibility, not a detected ocean. The same gravity that may have helped this planet to retain an atmosphere could create an enormous barrier to spaceflight. A gravity well represents the gravitational potential surrounding an object. The deeper it is, the more energy is required to escape. Surface gravity would be approximately 1.87 times Earth's. Life could adapt, and ocean buoyancy would offset much of the increased weight. The real problem begins when a civilization tries to reach space. Earth's escape velocity is approximately 11.2 kilometers per second. On this planet, it would be around 20.1 kilometers per second, almost 1.8 times greater. Even entering orbit would be difficult. A spacecraft near the planet would need to travel at approximately 14.2 kilometers per second to remain in orbit, compared to only 7.9 kilometers per second near Earth. These differences may not sound enormous, but rockets are governed by an exponential equation. In his 2019 paper, Spaceflight from Super-Earth is Difficult, Michael Hipke considered an idealized chemical rocket with a specific impulse of 350 seconds. Under his simplified model, escaping Earth requires an initial to final mass ratio of approximately 26. For LHS 1140b, the corresponding ratio would be approximately 350. For every ton of final mass, the rocket would theoretically begin with about 350 tons. Even that is an impossible lower limit because it must include the rocket's structure. Real rockets use multiple stages, and reaching orbit requires less energy than escaping completely. More efficient engines would also improve the calculation. Hipke did not conclude that chemical spaceflight from a planet like LHS 1140b would be impossible. His paper suggests that chemical rockets could remain feasible on rocky planets with masses of up to approximately 10 Earth masses. This planet falls below that limit. Its inhabitants wouldn't be permanently imprisoned by physics, but their equivalent of a Sputnik might require a much greater industrial effort than ours. If the planet is tidally locked, it would also provide almost none of the rotational assistance that rockets receive when launching eastward from Earth. A civilization might eventually need nuclear propulsion, beamed energy systems, or electromagnetic accelerators. Its first satellite could therefore arrive much later in its technological history. It might master radio, computing, and nuclear energy while remaining confined to its planet for centuries. A civilization on this planet could be technologically sophisticated and detectable even without achieving spaceflight. Radio transmitters and lasers don't need to overcome escape velocity, while industrial pollutants, artificial illumination, and waste heat could produce technosignatures. The gravity well might suppress space travel without suppressing evidence of technology. At 49 light years, ordinary radio and television leakage comparable to ours would be extremely faint. We would be more likely to detect a deliberate narrowband beacon or a powerful radar beam directed towards us. Earth's radio emissions have already reached this system. An observer there today would receive emissions from Earth as it was around 1977. But arrival doesn't mean detectability. Our ordinary broadcast would probably be far too weak. We have a dedicated video where we discuss human technosignatures. I invite you to check it out. Future observations must determine whether the helium escape is variable, constrain the Lua atmosphere, and establish whether this is a world, an icy planet, or something else. Its proximity also makes the system a rational SETI target. Gravity alone cannot completely solve the Fermi paradox. Leaving this planet would be difficult, but not impossible. The galaxy also contains smaller planets, and the expansion argument requires only one civilization to develop interstellar travel. Furthermore, a civilization doesn't need spacecraft to transmit radio or laser signals. High gravity is therefore better understood as a possible filter between technological intelligence and interstellar civilization, not as a complete explanation for the great salience. Nevertheless, it challenges a hidden assumption that intelligence naturally leads to a spaceflight and that spaceflight inevitably leads to the expansion across the galaxy. Humanity may have been fortunate. Earth is massive enough to retain a life-supporting atmosphere, but small enough for chemical rockets to escape. Our ability to reach space may be a form of planetary luck. If life exists on LHS 1140b, it would have evolved under almost twice Earth's gravity, perhaps on a water-rich world and beneath an atmosphere whose upper layers are losing helium. If the planet is tidally locked, its inhabitants might live beneath the dim red light of a star that remains almost fixed in their sky. If intelligence emerged, it could have followed a path very different from ours. It might discover radio without developing practical rockets. It might understand the stars, while remaining unable to reach them. Its greatest barrier might not be intelligence, energy, or time, but the gravity of its own world. If you made it this far, please consider subscribing to the channel and giving this video a like. Do you think that deep gravity wells of super-Earths could be one reason we have not encountered extraterrestrial civilizations? Let me know in the comments. We also have a full video dedicated to the Fermi paradox, which I invite you to check out. Thank you for watching and for being part of this growing community. That's it for now, and remember, the truth is out there.